Okay, so we're going to start with 1.2 graphs of equation. So first we're going to start with question in two variables and ordered pairs. A relationship between two variables is expressed as an equation in two variables. An example of this would be y equals 7 minus 3x. This equation has x and y. An ordered pair is a solution or a solution point of an equation in x and y when the substitution x equals a and y equals b results true. An example of this would be the point 1, 4 is the solution of y equals 7 minus 3x because 4 equals x minus 3 times 1, and this results in a true. Example 1, determining solution points. Determine whether part A, 2, 13, and B, -1, -3 lie on the graph of y equals 10x minus 7. In part A, we'll put 13 and 2 into the equation. 13 equals 10 times 2 minus 7. And when we solve this, 13 equals 13. Since this statement is true, then 13 is a solution. But on the other hand, if we put -1 and -3 on the graph equation, this will result in a false statement. Therefore, this ordered pair is not a solution. Basic technique for graph sketching. The basic technique used for graph sketching is an equation, and it's called a point plotting method. The steps are, when possible, isolate one of the variables, construct a table of values showing several solution points, plot these points in a rectangular coordinate system, connect the points with a smooth curve or line. Example 2, sketching the graph of an equation. So we're going to sketch 3x plus y equals 7. So first we'll isolate the variable y. So we'll get y equals -3x plus 7. Next, we'll construct the table with several solution points of the equation. For example, when x equals -3, we'll plug that into the equation and we'll get a result of 16, therefore implying that -3, 16 is a solution on the equation. And here is a chart of different solutions. So when we're sketching the graph, we'll plug in all these points, and after plugging in these points, we connect the lines shown below. This is the equation y equals -3x plus 7. Sketching the graph of an equation, but instead we're going to do a parabola this time. Y equals x squared minus 2. So the solution will obviously just plug in anything for x, and we'll get the return for y, and we'll find the solutions. Then we're going to plot the points. We plot all these points, and then we could just make a curve. Intercepts of graphs. Solution points of an equation that have 0 as either the x-coordinate or the y-coordinate are called intercepts. On the graph is when it touches the x or y-axis. It is possible for the graph to have no intercepts, one intercept, sorry for the typo here, one intercept or several intercepts, as shown below. This one only has one intercept, but no x-intercepts, one and y-intercept. This one has 3 x-intercept and one y-intercept, as shown here. The intercepts the x-axis 3 times, one's on the y-axis. This one has 1 x-intercept and 2 y-intercepts, and this has no intercepts. How do we find the intercepts? Well, the steps to finding the intercepts is when we're finding the x-intercept, we're going to let y be 0 and solve for the equation for x. We're trying to find the y-intercept, we'll let x be the 0 and solve for the equation y. Example 4, finding x and y intercepts. So first we're going to find the x and y intercepts of the graph, y equals x cubed minus 4x. To find the solution x-intercepts of the graph, we're going to grab the equation and let y equals 0. So when we plug in y, we'll get x equals 0 and x squared minus 4 equals 0, and x squared minus 4 will result in plus or minus 2. So x will equal 0 and x will equal plus or minus 2, and we plug them into points. It will be 0, 0, 2, 0, and -2, 0, shown in this figure here. Now we're going to look for the y-intercepts. We're going to plug in y as x, 0 as x. So here you can see that 0 is plugged into this equation for all the x's. and we'll end up with 0. So the y-intercept is 0, 0, shown on the graph here. Symmetry. Graphs of equations can have symmetry with respect to one of the coordinate axes or with respect to the origin. Symmetry with respect to the x-axis means that when you fold the Cartesian plane along the x-axis, the portion of the graph above the x-axis coincides with the portion below the x-axis. Symmetry with respect to the y-axis or the origin could be described in a similar manner. The graphs below shown these three types of symmetry. This is x-axis symmetry, this is y-axis symmetry, and this is origin symmetry. Graphical test for symmetry. A graph is symmetric with respect to the x-axis if whether x, y is on the graph, x negative y is also on the graph. A graph is symmetric with respect to y-axis is whenever x, y is on the graph and negative x and y is on the graph. A graph is symmetric with respect to the origin if whether x, y is on the graph and negative x and negative y is also on the graph. Here's an example of the graphical test of symmetry. So here we have the equation y equals x squared minus 2, and it's symmetric with respect to the y-axis because xy and negative xy are on the graph of y equals x squared minus 2, as shown on the table and on the figure. Algebraic test for symmetry. The graph of an equation is symmetric with respect to the x-axis when replacing y and negative y yields an equivalent equation. The graph of an equation is symmetric with respect to the y-axis when replacing x and negative x yields an equivalent equation. The graph of an equation is symmetric with respect to the origin when replacing x and negative x, x with negative x, and y with negative y yields to an equivalent equation. Here's an example for testing symmetry. So we're going to test y equals 2x cubed for symmetry with respect to both axes and the origin. So the solution here will be first grabbing the equation, then plugging in the negative, and since it does not result with the equivalent equation, we're going to test for the y-axis, and we're going to plug in that negative x, and it does not result in the equivalent equation. So now we're going to plug it in with the origin. We're going to plug in negative y and negative x, and it does result in the equivalent equation as seen in the original equation, and therefore this graph and equation is only satisfying the origin symmetry. As you can see on the graph, you could pretty much tell that it won't satisfy the x-axis or the y-axis, but you still might want to check it. Circles. A circle is a set of points x and y in a plane that are in the same distance r from a point called the center hk, as shown at the right by the distance formula shown here. By squaring each side of this equation, you obtain the standard form of an equation of a circle. For example, for a circle with its center at hk equals 1, 3, and the radius y equals 4. You plug it into this equation and you result in 16. Standard form of an equation of a circle: a point of xy lies on the circle of the radius r and the center hk if and only if this equation is true. From this result, the standard form of an equation of a circle with radius r and the center of the origin hk equals 0, 0 is x squared plus y squared equals r squared. Example 6. Writing the equation of a circle. The point 3, 4 lies on the circle whose center is at -1, 2. As shown in the figure 1.18, write the standard form of the equation of the circle. So the radius of the circle is at the distance between -1 and 2 and 3, 4. So we're going to plug in the points, and we're going to substitute x, y, and hk, and then we're going to simplify this down, and we're going to get radical 20. Using hk and -1, 2, and since we know that now the radius is radical 20, we're going to plug it into the original different equation, the equation of a circle, and then we're going to end up with 20. and this is we're going to end up with 20 on this side, and then we're going to simplify this part, and this is your standard form. Maximum weight, example 9. The maximum weight Y in pounds for a man in the United States Marine Corps can be approximated by the mathematical model Y equals 0.040 x squared minus 1.11x plus 3.9, and we know 58 is less than or equal to x, but x is greater than 58 is less than or greater to x, and x is less than or greater sorry, let me repeat that. 58 is less than or equal to x, and x is less than or equal to 80, where x is the man's height in inches, in. So first, we're going to construct a table of values that shows the maximum weights for men with heights of 62, 64, 66, 68, 70, 72, 74, and 76 inches. And then next, we're going to use the table of values to sketch a graph of the model, then use the graph to estimate graphically the maximum weight for a man whose height is 71 inches. Then we're going to use the model to confirm algebraically the estimate you found in part B. If you want to take a while to do this, I'll give you a few seconds. Here is the solution to example 9. So for part A, we're going to use a calculator to construct a table as shown on the left. And then for part B, we're going to use the table of values to sketch the graph of the equation as shown in figure 1.19. From the graph, you can estimate that the height of 71 inches corresponds to the weight of 198 pounds. To confirm algebraically the estimate you found in part B, substitute 71 for x in the model. Here you can see, so the graphical estimate of 198 pounds is fairly good.